really happy and honored to visit Odense here. I have visited, of course, Asker before when he was in the competing institution in Lyngby. As you can probably tell from my accent, I'm not really a Texan, which is sort of where I am. I'm from Sweden, and I spent 2 years of my PhD work with Jens Nørskov at Lyngby at Nordita. Okay, so I know a little bit of Danish. So when I sent in the abstract for this talk, I crowded it with a lot of stuff of the most recent research I'm doing. But then when I was reading the description of this wonderful institute you have, I realized it's probably better to keep my talk on a more general level. So I'm going to be here both today and tomorrow. So if you want to know anything more about this topic that I a little bit superficially will go over, feel free to contact Asker and set up a meeting with me. So here it will now be on a more basic level. And the topics is going to be these kind of topics, a little introduction, and then at the end, I'm going to talk a little bit about some very recent work. And a characteristic feature of all our research having to do with plasmonics, and I will soon tell you what the plasmon is, okay, is sustainability. We are really driven by trying to make an impact on clean environment and sustainable life. And you will see that when we come to the photocatalysis in particular. Okay, so what is a plasmon? Okay, sorry, Asker, you know this. And a plasmon is what's called an incompressible oscillation of the conduction electron in a metallic nanoparticle. So a metallic nanoparticle, it gets its properties, electric conductance and heat conductance, from free electrons. The atoms give away electrons which sort of form an electron gas. And because the distance between the electrons is very, very small, it's incompressible. You can compress it, but not with forces from electromagnetic radiation. So it's basically incompressible. So the simple answer here of what a plasmon is, fill the balloon with water and start hitting it on one side. You're going to see incompressible oscillations. So in the metallic nanoparticle, you can do a rigid displacement of the conduction electron to one side. You generate surface charges, and that provides a restoring force. And if you solve the Schrödinger equation and Newton's equation, you'll find that you have sort of a harmonic oscillator. It goes back and forth. And if you drive this now with electromagnetic radiation, with the polarization in the direction of this oscillation, you can resonantly drive it. It's like a swing. If you hit the swing with a little baby in at the right frequency, you're going to get more and more amplitude. So that's what the surface plasmon is. Now, because there are so many electrons in a nanoparticle, perhaps 1 million, it has a very large cross-section. So a plasmon can be excited. It grabs light very, very efficiently. I'm going to come to that when we come to sustainability. And another consequence of this large cross-section is that you are getting surface charges, okay? And surface charges give rise to electric fields. So if you drive this plasmon up to a large amplitude, you can get very, very large surface charges, and then you can get very large local fields at the surface, and these are called hotspots, and I will talk a little bit about that. Okay, so now I'm going to do a little bit more than an animation. I'm going to show you a simulation. This is something called finite difference time domain simulation of the local electric field in a nanoparticle when you hit it with the electromagnetic pulse. I'm going to use a particular nanoparticle called nanoshell that Naomi Hallas invented, which consists sort of a dielectric circular core like silica, and then you have a thin metallic shell. It has a lot of interesting properties. So I'm going to put that in vacuum, and I'm going to cut a plane through that nanoshell, we call it. Okay, and I'm going to plot as a function of time everywhere in the plane the total electric field. So the total electric field is going to be the incident pulse we see here, but then it's going to be the field generated by the nanoparticle. So this simulation is vacuum. It's done using something called absorbing boundary conditions. Okay, here's the light pulse come. It has a chirp. It goes through with speed of light. This is about 100 nanometer particle. So you can see here, the light pulse is gone, But these plasmons are continuing. In fact, they are continuing for up to perhaps a picosecond, depending on the radiance of the modes. And this is all because with this pulse, we set a lot of plasmons in motion. You can think about the pulse like a hammer hitting a bell. Each bell, depending on the shape of the bell, there's going to be a distinct tone of the bell, because you hit it with a hammer, you excite overtones, and that's exactly what you do with the plasmon. So this was just, I'm still on the introduction here. The higher modes here that survive the longest, they're high multipolar whispering gallery modes. They don't radiate, so they can live for a very long time. Okay, so now I'm going to show the hotspots. Remember, I showed you that you can get very large electric fields at the surfaces when you resonantly drive a plasmonic nanostructure. So it's a different student this time. We're going to use a CW, continuous wave excitation, with a frequency tuned to the plasma resonance of this nanosphere. And I'm going to plot in this plane the electric field all over this plane, but in CW excitation. So you see something interesting here. So you see here, and the diameter of the sphere is 60 nanometer. You can see here the CW wave goes through, and you can see here that at the poles of this sphere, you get a field enhancement. Okay? And this is interesting, because the sort of volume of the area where we have this field enhancement, these peaks at the poles, is about 5 nanometer. So we have actually accomplished sub-wavelength light amplification. So we are focusing light. So with the lens, you can only focus light down to a wavelength, okay, or quarter wavelength, whatever, because of the wave and phase, the conjugate properties of these properties. But here with this plasmonic nanoparticle, I got this very big amplification of light, a factor of 10 approximately amplitude. Let's see now when we have 2 nanoparticles, okay, same spheres, okay, same wavelength. Let's see what happens. So light, we normally think about 2 laser beams that will be twice as intense, okay? But let's see what happens when we look. When we have these 2 nanoparticles next to each other, we get an enormous amplification of the intensity in this gap here. This amplification is about 100. Here it was about 10. So we don't get 20 here as we would have assumed with superposition. No, we get 100. So something fundamentally happens, okay? And that is that the plasmas start to interact. So this is the first sort of major thing we did in plasmonics. It was developing sort of an understanding of how come plasmons in 2 separate nanostructures, how can they interact and give the interacting systems so completely different properties. In this case, a factor of 100 amplification of the field instead of a factor of 10. And what we showed here was that if you have a plasmonic structure, we can write down the equations for those particles, and we get something called the secular equation. And what we showed, what was interesting, but the mathematical structure of that equation that we got was, we call it isomorphic, but let's say better, equivalent to the mathematical structure of the molecular orbital electronic structure problem, molecular orbital theory. The meanings were different. In molecular orbital theory, you talk about expansion coefficients, blah, 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 and orbitals. In a plasmonic structure, you talk about plasmon amplitude. So what happens when you have this interacting plasmonic structure is that you form a bonding, just like your 2 hydrogen orbitals, they interact to form bonding and antibonding orbitals. So we form this sort of bonding orbital where we have very large dipole moment. So this is sort of the reason why we have these large field enhancements in the dimer. And more importantly, it sort of brings this plasmonic problem sort of into more mainstream science like molecular orbital theory and quantum mechanics. So that was my introduction, and now we will be a little bit more specialized. I'm going to talk about 2 recent hotspot applications, okay? And they have to do with doing single molecule spectroscopy. So why that is important is that when you do single molecule spectroscopy, you don't have inhomogeneous broadening, so you can isolate pure quantum mechanical effect and sort of isolate the classical effects. And this first paper, this is from Naomi Halla's group, published a couple of years ago, is something called surface-enhanced coherent anti-Raman spectroscopy. It's a kind of abbreviation that you cannot say too fast. But anyway, so I'm not going to go to the detail. This is a legitimate spectroscopy. It's a nonlinear spectroscopy. And the amplitude for the signal of this spectroscopy turns out to scale basically with the 8th power of the amplitude of the electric field. Okay? Remember in that dimer movie I showed you, I showed that the electric field amplitude in the dimer junction was a factor of 100. Okay? So suppose we have a spectroscopy that goes to the 8th power of that amplitude, well, then we here have 10 to the 16. So this plasmonic nanostructure with the ability to provide sub-wavelength focusing and these very large field intensities can actually make this type of amplify this type of spectroscopy to such an extent that you can distinguish an individual molecule. So, and this happens from our group. There are many other groups that are reporting single molecule spectroscopy. And I just wanted to show you this because I wanted to address a little bit how do we prove single molecule spectroscopy. So several ways of doing that. The most the most robust method is the bianalyte method, and you can read about that in this paper. But it's basically if you have if you now take a mixture of two molecules, A and B, okay, and you pour that over the structure, okay. So if you are reporting spectroscopy from a single molecule, you will see either no signal or signal A or signal B. You will never see A and B, okay? So there's more mathematics to this, and you do this now with controlled variations, etc. It's a statistical approach, but that is how we were able to prove that, in fact, we had single molecule spectroscopy here. We never saw the simultaneous appearance of spectral lines A and B. So here's another one that is very challenging. This is also from Naomi Halla's group. Okay, this is surface-enhanced infrared absorption. This is one of the most promising spectroscopies because it's very easy to interpret. But the signal for this spectroscopy is square in the field enhancement. So it's not like CCARS, factor of 8 of the field enhancement. It's square. But this is something that everybody wants to do because if you could push this SEIRA, surface-enhanced infrared absorption, to the single molecule, you have a wonderful chemical method where which you could really do chemical analysis without knowing the substance you put in. You could do that for an arbitrary mixture. So there's a lot of research that. So here is the sort of plasmonic antennas we make, and you can see they are pretty big, but they have a very narrow gap. So again, the Plasmon hybridization test, as we want, these very narrow gaps. So if you calculate the field intensities, sort of if we look now, this is successive applications here. We have sort of a narrow junction here, that here we have the surfaces here. You can see that the field enhancements we get here in the junction and on the bearings and on the antennas, they range from 10 to the 7 to 10 to the 2. So what we did with this, using the bianalyte method, the statistical methods like I showed before, showed that this particular antenna, published last year, were able to detect 500 molecules. We want single molecule. So in other words, we are working on boosting the efficiency of this antenna by making the junction smaller, the antenna larger by 15 times. Then we will be at the single molecule level. Now, we are not the only people doing that. This is one of the holy grails of all plasmonics research, is being able to do single molecule SEIRA. So, and we are not there yet, but I hope to be there soon. Okay, so one of the reasons I've been such a big admirer of Asker for many years has to do with quantum plasmonics. But it's a little bit too much formalism, so I decided to skip that subject and focus on another related topic called molecular plasmonics. Okay? And I said before that metallic nanoparticles can have plasmons, this incompressible motion of the conduction electrons. But certain molecules can have plasmons too. They are quantum mechanical plasmons. We cannot use E&M to describe them, but they have the properties of plasmons that we like. And this started out as a theoretical investigation, and we were interested in graphene. As many of you may know here, graphene in its undoped states has no plasmonic response because it has a semi-metal, but if you dope it, you get sort of a tunable plasmon energy. You also may know that if you take doped graphene and you shrink it, okay, you blue shift the plasma resonances. So graphene is an interesting plasmonic material. Now the problem here is that the plasma resonances are in the mid-infrared, and that's not where we want to be. I will show you later we want to have plasma resonances that can overlap electronic transitions, okay? So that's not in the infrared. So we actually, in this paper here, we show that we took this sort of ultra-small graphene. So this would be like 4 benzene rings. And then, of course, to get it converging for a small system, we had to terminate with hydrogen. So this is sort of the picoscale graphene. It's also a molecule, a chemical molecule known as a polycyclic aromatic hydrocarbon, and there's a large number of different such molecules. In the undoped case, this orange line here, there's no plasma resonance. But now when you either remove an electron or add an electron, you get distinct plasma resonances. Okay? They're collective excitations. They are plasmons, molecular plasmons. So they have a lot of these properties that we're interested in. The interesting thing here is that it's enough to do it with one electron. Okay? So here we have a system where adding an electron or removing an electron, we immediately go to a plasmonic system. We have the possibility here to use this as ultra-fast switches. Okay, so here is an experiment also done from Naomi's group, from Rice, where they experimentally verify this sort of color change, this onset of plasmonic behavior when you add or remove electrons, in this case adding electrons. And this is a picture, this was done electrochemically, this is a picture of the color change. This is in the neutral state, this is in the negatively charged state. There's the measured spectrum, here's the theory. So it completely verified the theoretical predictions. We have these molecular plasmons, a very interesting possibility now for changing light harvesting plasmonics. We can do a device of it. In fact, this is a multi-state electrochromic pixel. So typically pixels are red, white, and blue, well, some colors, and you turn on different magnitudes to activate different colors. But here we can actually do this because we can change the color by either removing or adding an electron. We can build a black device by just taking a mixture of these kind of things, or we can have a multi-state color changing pixel. And we recently published an interesting investigation on the lifetime of these molecular plasmons. And what we show here that the lifetimes of molecular plasmons is actually longer than typical plasmons. It's about 10 picoseconds. So it's a pretty stable system. Okay, so now the last and most important thing here. So I have 10 minutes? Yeah. Okay, so this is going to be light harvesting.
More, maybe.
Sorry?
You have a little more.
Okay, very good. So why would we go plasmonics if we do light harvesting? Well, because they are giant light harvesters, and this has to do with the field enhancements. So what I'm showing here, this is what's called the pointing vector. Okay, so this is sort of the flow of energy from a plane wave hitting a nanoparticle, in this case an aluminum nanoparticle. So this is off resonance. So you can see here this nanoparticle off resonance absorbs a little light. We have a shadow here behind the nanoparticle, a shadow which of a physical cross-section about half the physical cross-section. So this is off resonance. We have this particle absorb light. Now, if light has the plasmon frequency, if you are on resonance here in this aluminum particle, that would be 8.8 eV, we see something very interesting. In fact, that this nanoparticle sucks in light from an area which is several orders of magnitude larger than the physical cross-section. They are enormous. They attract light. Okay, so the shadow behind this particle is several orders of magnitude larger than the physical cross-section. The physical reason for that is very simple. So we have very large surface charges. Remember how this plasmonic nanoparticle induce surface charges, and those surface charges are long range. Okay, so when you solve this problem mathematically, the field from the induced surface charges have to match the incident field. So that's why they have these enormous cross sections. Now the importance of this is that we can make perfect adsorbers. We don't need to cover my surface completely with plasmonic nanoparticles. I can have a very dilute coverage, perhaps a 1% coverage physically of plasmonic nanoparticles, and I will harvest all light coming in. So they have this unique light harvesting possibilities. So I'm going to talk about a few applications of that now for the remaining talk. And this has to do with hot carriers. So when you remember the movie I showed in the beginning, we came in with the pulse in this FTTD simulation, and we saw plasma response, and eventually it died out. So why does it die out? Well, it dies out for two reasons. It can emit radiatively photons, that's like an antenna effect, or it can generate electron-hole pairs. These are called hot carriers. And that's called non-radiative plasmon decay. These hot carriers, unless harvested, will eventually result in heating. And Naomi will talk a lot about interesting photothermal effects. But the point here is we are going to have these hot electrons and hot holes that sort of physically are going to be outside the nanoparticle because they have higher energy, they are closer to the vacuum level, and they can do things. They can be injected, transferred into acceptors, or they can use in chemical reactions. So, and this plasmon-induced hot carrier generation is extremely efficient because you have this giant cross-section of the plasmonic nanoparticle. So now, very quickly, this is paper we just published, they have a finite lifetime. They don't survive, they don't stay hot for a long time. They stay hot for about a picosecond. So when you want to harvest them, you have to either have a CW illumination, continuous, or you have to have a very quick transfer. And here you can see a little bit about, this is a very complicated calculation where we look at the hot carrier distribution, the hot electrons and the hot holes as a function of time after excitation. You can see how they carry, multiply, and thermalize. That's just for the experts in the audience. Okay, so what can we do with them? I'm going to show you photodetection, I'm going to show you photocatalysis, and I'm showcasing this review article, which is obsolete now, okay? This field is moving so fast. So the paper from 2015 is no longer relevant. Photodetection, okay. This was the first paper. So we put a plasmonic nanoparticle on the silicon device, and when we now excite the plasmon, and the color here we tune by changing the shape of the nanoparticle, that's not interesting. When we excite light, we are generating hot electrons who can go into the substrate. You can detect them as a current. This device has to be covered by something conducting and transparent because if you didn't have sort of a backflow of electrons here, you would charge the particle and you would stop, okay? This kind of hot electron-based photodetectors can have a quantum efficiency of 20%. They are not limited to the band gap. We are not, although we use silicon here, we are not doing an excitation from the valence band to the conduction band. No, we are doing direct injection in the conduction band. We can do chemistry, my last topic. And I'm not a chemist, but fortunately I collaborate with people who know chemistry. This is Emily Carter at Princeton. And this is basically the poor physicist's view of what happens here. You put the molecule on the surface, you will have bonding orbitals below the Fermi energy and the bonding levels above the Fermi energy. If your surface has no hot carriers, you can have no hole transfer, no electron transfers. But if you create hot carriers, you can have redox, you can have electron and hole transfer, okay? So we did that in Naomi's group. So now we did this experiment showing that, in fact, you could dissociate H2. And that's actually something quite remarkable because an H2 for a physicist is the helium atom, okay? You look at it from a distance, it's 2 electrons. So it's very difficult to dissociate this 4.6 eV dissociation. Now, if you form an H2 minus, okay, then it's very easy to dissociate. It auto-dissociates because that electron goes into an anti-bonding level. So long story short, we use this model reaction just to prove the existence of hot carrier-induced chemistry. And it worked. And here's one of the more recent papers we did. We actually showed you can do it on aluminum, okay? And that's the hallmark of our research is to do sustainable materials. Gold plasmonics is great, but aluminum plasmonics is greater because it's very cheap. So what we did here, in fact, we show that you can make these aluminum nanocrystals in enormous groups. And when you turn on light and turn off light, you get HD dissociation. You measure HD, so that's then the dissociation product, and it's very efficient. So that got us very interested. Okay, we saw that we can actually do catalysis, but how can we make catalysis efficient? Okay, aluminum and gold by themselves are great plasmonic materials. Okay, as would be copper and silver, but they don't have D bands. They are very poor catalysts. So we tried to come up with a kind of concept which involved the light harvesting of plasmonic nanoparticle with the catalytic performance of transition methods, which would not be light harvesting. And this is the antenna reactor concept. And I'm going to talk now about a few very quick applications of this antenna reactor concept. So the idea is this. You build a plasmonic antenna with this enormous cross-section. That plasmonic antenna is going to generate a large local near field. Okay? So if in this near field now we put a catalytic reactor, then the light harvesting purposes of that plasmonic antenna is going to focus light into the transition metal reactor. So you can tune this concept independently and you can do catalysis. So here was the first. Again, I'm going at the record pace here. I can ask any questions. The first thing was in 2016. This was an aluminum nanoparticle, not as a disk, it was a sphere, and then we put palladium nanoreactors around it. And what we saw here is that we can get very high selectivity for a chemical reaction called acetylene dehydrogenation. So basically, from this chemical compound, you want to make this, but not this, okay? And doing it on these catalytic reactors increased the selectivity in order of magnitude to get this compound. Here we have CO2 reduction. So normally CO2 reduction, CO2 of course is a horrible greenhouse gas. So CO2 reduction involves making CO. That sounds really stupid because CO is poisonous and very bad, but in fact CO can be mineralized. You can bind CO to metal. So making CO out of CO2 is a way of actually getting rid of CO2. And we saw that on a aluminum copper oxide antenna reactor. You can read about it here. I understand my talk will be available somewhere here. Okay, so we continued, and last year we developed a lot of new types of antenna reactor. We like the aluminum plasmonic antenna. It has large cross-section, it's abundant. And then these reactors we can use expensive materials for that because there is very little volume. Most of it is the antenna, and then we can have the catalysis happening. So then this paper that Asger referred to, the science paper we had last week, was now a very fundamental study of how does this catalysis, how does a hot carrier catalyze a chemical reaction? Okay, all of you know that the rate for a chemical reaction can be described as sort of an Arrhenius equation. So you have some activation barrier, which is sort of the potential energy landscape of the chemical reaction, and you have the temperature. Now, if you illuminate a nanoparticle, you have two effects. You are going to change the activation energy, I will show that very soon, but you're also going to change the temperature of the reactor because you have light absorption. So the question is, how can we isolate these two effects? The effect on the energy barrier and the effect of the temperature. So the reaction we did is an important reaction. It's for ammonia decomposition. And this is important for a number of reasons. If you want to, ultimately we want to have a hydrogen economy. We want to drive cars and everything with hydrogen. But it's very dangerous to store and transport hydrogen. So for instance, Toyota is developing ammonia as a storage medium for hydrogen. Ammonia smells, but it doesn't explode, okay? So it's a benign way of doing it. So anyway, long story short, there are, in this ammonia decomposition, is an extremely well-studied reaction with normal catalysis. There is two steps that limit the performance. It's the bond scission, step number 2, and it is the step number 6, which is the associated desorption. And they have different activation energy. That the bond scission is 0.2, the associated desorption is 1.2. So here we did it first initially, just showing that photocatalysis, doing it with light, we had much larger efficiency, okay? Way much larger efficiency in this process. Okay, and then the work started. And that was now to map that light-dependent activation energy. So it took 1 year out of Lina and Zhou's life to actually go for a particular wavelength on different intensities, measure the activation energy, okay, compensating for the temperature, etc. And here is sort of, this plot are just cuts. Here is now a 2D contour showing the effective activation energy for this chemical reaction as a function of light intensity and light wavelength. So if you go here in dark, if you have a light intensity 0, the activation energy is 1.2. That's the bonds, the associated desorption. Now, if you go to higher intensity, and particularly go to 500 nanometer, you see here that the activation energy is 0.2. That's a factor of 5 change in the activation energy in an exponent. That means it's to the power of 5. This is a huge effect, okay? And knowing this light-dependent activation energy now will allow us to optimize this chemical reaction, because for efficient catalysis we need both low activation, etc., but we also need temperature. But now we have isolated. We know exactly how this activation energy in the Arrhenius equation depends on light. Last example here is another very important reaction, and this is nitrous oxide. This is a really horrible, we don't hear much about it because it's more up in the high atmosphere, stratosphere, but it's a very bad agent for ozone depletion. So it's a very bad gas, very bad greenhouse gas, not down here, but up there. But it's also a great fuel and a great way of storing air. If you can decompose N2O, you essentially get air. Well, you get a little more higher oxygen. So it's actually used, people are thinking about it when they go to Mars, perhaps to bring it. It's a great way of storing it, and it's a great fuel. So this has not been submitted yet, but we show here that, in fact, an aluminum iridium antenna reactor provides a very, very efficient catalyst for this ammonia. In fact, we can get out of catalysis. The interesting thing here, since we know that activation energies can change, on gold, on the aluminum gold, we have a change in activation energy, but in aluminum iridium, there is no change in activation energy. And in fact, it can be very efficient with catalyst. And remember here, we use very little iridium. Iridium is expensive, but there is almost no, I mean, the fraction of micropercent iridium. Okay, so in a very superficial way and too fast, okay, I covered a lot of subject that I hope will make you a little bit interested in plasmonics, and it ranges from plasmon hot carriers to photocatalysis. So with that, I stop and take any questions, or we wait.
Please, yeah. Thank you, Peter.